So how do I use the second derivative test to determine concavity? Well, remember the second derivative is the slope of the first derivative. If a function is concave up, where f prime of x is increasing, the slope of that graph is going to be positive. And so if the double derivative, or the second derivative, is positive, the graph of the original function is concave up. Similarly, if the double derivative is negative, that means the derivative is decreasing, therefore the function is concave down. Where f prime of x equals 0 on this point of inflection, potential, there has to be a switch, okay? An inflection point has to be a switch. Inflection change isn't necessarily at a point. We might call it a point of inflection, but an inflection change could be an asymptote. An asymptote could be a spot where the derivative, the double derivative is 0 or undefined, and as long as the concavity of the original function switches. All right, so for f of x equals x cubed, we're going to graph f of x and f of x on the calculator, and let's just investigate where the graph is concave up and down. Okay, so I'm going to put in x cubed. And let's just maybe put in, I don't know, how about -2, -3. I'm going to make a really small window. And maybe -30 to 30 so I can see the whole graph. Let's see how that looks. Okay, so there's x cubed. To me, it looks concave down here, then concave up here. Okay, in order for the function to, that's where it looks concave down. Let's graph the first derivative with this. Okay, so I'm going to first take a look there. I'm going to go into, and I'm the first derivative, which is 3x squared. I'm going to go ahead and make it a different kind of line. I'm going to make it a thicker line. Okay. What I want to point out to you is from negative infinity to 0, the derivative is decreasing. If we go back earlier in our notes, what that tells us is that f prime of x decreasing from negative infinity to 0. What that tells us then is concave down. That's what it looked like down. F prime of x is increasing on the interval 0 to infinity. What does that mean about the function? That it is concave up. All right. So if that is true, let's now take a look at the double derivative. So what the derivative is, where the double derivative is positive, that's where the original graph is concave up. So let's take out our derivative and write the double derivative, which would be 6x. Okay. According to this is the second derivative. F double prime of x, the second derivative, is negative. It's below the x-axis here. It is 0 on the interval negative infinity to 0. So that is another way of telling us when the double is negative that the graph of f is concave down. And we see there's our graph of f concave down. So f of x is concave down there. Let's take a look over here. from 0 to infinity, double prime of x is greater than 0. From 0 to infinity. That means that x is concave up there. So you might be asking yourself, well, I came to the same conclusion. Why does it matter? It matters because sometimes I'm not going to have all of the functions. Sometimes I will give you the first derivative, so you can't use the first derivative. Sometimes I'll only give you the second derivative. So you should be able to use both the first and second test, or of the derivative. And the picture of the derivative, you're going to want to think of it in this way. Oh, where's the function concave up? I need to look at where this is decreasing. So you should be able to tell concavity with both the first and second derivative tests. All right, let's then put it all together for a function. Okay, so what we're going to do is I'm going to actually do two charts now. I'm going to do a chart with the first derivative to check for extrema, but then I'm also going to do a chart with the second derivative, and my second derivative is actually going to help me check for concavity, and I'll also tell you how it really checks for extreme as well. So let's do this example. I'm going to find the first derivative. I'm going to go to this in a second and find all relative extrema and points of inflection. So I'm going to find the first derivative. It is f prime of x equals squared minus 6x minus 12. I am going, this is not undefined anywhere, but to find a critical potential extrema, I'm going to set this equal to 0. And so I'm actually going to pull a 6 out first. And then I'm going to factor this. So the criticals are at x equals 2 and x equals -1. And then from the other day, what I do then is I put this in a sign because I want to figure out what my derivative is doing. Is it increasing or decreasing? Okay. So over here, I'm going to pick a value. I'll call it, well, here's my intervals. I have -infinity to -1. I have -1 to 2. And then I have 2 to infinity. And then we're going to describe what the derivative's doing there and what that tells us about this stuff. So if I picked like -2 and I put it in this expression here, I would have, well, 6 is always positive, so I'm really just looking at these two. The negative, this negative and this negative. A negative times a negative is a positive. If I picked a value between -1 and 2, suppose 0, and I add it in, I'd get a negative times a positive, which is a negative. And then if I picked something larger than 2, I'd plug it in, and I get positive times positive, which is positive. So I go up to my table. What that means then is this is greater than 0. If the derivative is greater than 0, that means the function is interval. If the derivative is less than 0 or negative, it switches to decreasing. Okay, so let's think, guys. If the function switches from increasing to decreasing, what has occurred at x equals -1? That makes x equals a -1 is where a I'll get into this later, but we should also write a sentence about that. The reason why is because the derivative switches from positive to negative. State a reason with that. Going back to our last interval, the derivative was positive. When the derivative is positive, what that my function, my original, increasing. Okay, so then at 2 is a half. Switch from decreasing to increasing. I'm just follow my pen here. Decreasing, increasing, and so at x equals 2, a minimum occurs. The reason why is because the positive there. Okay. If I want to just point out something to you about the second derivative test, because this was just the first derivative. We're going to get into the second derivative in a second to check for inflection. But I want to something we're going to talk about more tomorrow. If I have a concave down interval, okay, concave up interval, looks like this, concave up interval, and I told you, hey, an extrema occurs on that interval, that extrema has to be a relative minimum, doesn't it? That's what this statement is saying. This double derivative being less than 0 means this is concave down. If I told you that an extrema occurred on a concave down interval, that extrema would have to be this. It would have to be a maximum. So what we see then is we can actually use the double derivative to confirm if something is a maximum or a minimum as well. But we'll spend some more time on that tomorrow. Okay, so this function, I decided I knew where maximum and minimum occurred. Let's now move on and look at the double derivative. Okay, so my original function was 2x cubed minus 3x squared minus 12x plus 8. Because I'm all blurry. The derivative is 8 squared minus 6x. Wait, what? Sorry. 6x squared minus 6x minus 12. We did that on the previous page. Now we're going to move to the second derivative. So we have 12x minus 6. All right, so to find inflection points are where the switches. So I'm going to see if I can see where the double derivative is 0 and if it switches signs there. So I go ahead and set this double derivative equal to, and I solve. So I get 6 equals 12x, and that means x equals 1. So now I'm going to do a sign chart with this. And actually, I don't need all these intervals. There's just one sign switch, which I'm checking if it's a sign switch. That breaks this into 2 intervals. I have the interval negative infinity to 2, and then the interval 1/2 to infinity. Well, I'm not going to test that. All right, so let's put in a that is to the left of 1/2. How about 0? If I put in 0, then I would get a negative number. If I put something to the right of 1/2, like 1, I would get a positive number. Okay. So then what that means is on the second derivative was negative. What that tells us is f of x is concave down on this interval. On the second interval, the second derivative is positive, and that means that the function is now concave up. So is there a point where the switches? There is. So I'm going to write this, and then tomorrow we're going to talk about how I'm going to use this with extremes. Let's call this point an inflection point. An inflection point is where the concavity of a function changes, and there is an inflection point 1/2. And the reason why I know that is that f double prime of x, the second derivative, switches from negative to positive there. Okay, so I think that's kind of enough to digest for today. And then, like I said, I'll formalize a little bit more how the second derivative also confirms maximums and minimums. But that gives me enough information how I can use kind of two separate, the first derivative and the second derivative, to find extrema and also inflection points.